There's this trendy theory going around, which posits that all perceived reality, including the universe, humanity, and for sure that AI slop you just ingested on LinkedIn, is a computer-generated simulation forged by some advanced civilization. This is known as simulation theory. Well, that's cute, because today's guest does a whole lot of simulation and ain't much of it theory. Dr. Eric Jankowski is director of and professor at the Micron School of Materials Science and Engineering at Boise State University, where he also leads the Computational Materials Engineering Lab. Dr. Jankowski uses simulation and computation, and in some senses digital twins, to drastically improve so much of our stuff, from semiconductors to solar cells to, I think Milk came up, to airplane wings, and who knows, maybe lab-built chicken wings in years to come. Bottom line, great chance you won't look at a lot of matter, and certainly your cotton t-shirts, in quite the same way, after absorbing the profound wisdom, technological prowess, and unrelenting passion of Eric Jankowski, PhD. Finally, the best way to keep enriching chats like this coming is the simple click of a mouse on that like button, for which we deeply thank you. Enjoy. Dr. Jankowski, welcome to the Recap Podcast, sir.
Good to be here. Thanks for having me.
Pleasure and a half. You were recently on business in Taiwan, if my homework is correct. What led you there?
This was a trip organized by the Idaho Department of Commerce. So we brought a bunch of business folks and university leadership from across the state. I think there were 17 of us in total. And we visited with 4 different ministries, 4 different universities, a number of semiconductor companies, startup accelerators, all around learning about opportunities around semiconductor education exchange, development, investment into Idaho, coordination among the Idaho universities, and just learning about Taiwan and the historic economic ties that it's had with Idaho.
Wow. Off the bat, most jarring to me. So we're not talking, so this is Department of Commerce, you said?
Yeah.
Is the genesis. Mm-hmm. This isn't Idaho to Denver or even New York City, Taiwan. Mm-hmm. Yeah. Were there sort of intermediary stops along a similar premise?
No, this was straight from Boise to Taiwan. And, well, I mean, we connected through San Francisco, but
got it. Okay.
No other stops on the trip. So we met with Micron, Taiwan. We went to the Taiwan Semiconductor Manufacturing Corporation. Some quick facts are that Taiwan is Idaho's second largest international trade partner after Canada. Micron is the largest foreign employer on the island of Taiwan. And there's a ton of semiconductor research and development and workforce development overlap inside of that relationship. And so Taiwan, as a global entity, is looking to invest more in semiconductor manufacturing in the United States. Boise is one of the places that they're looking to invest more money. And when we're talking about invest, right now the government of Taiwan has guaranteed $250 billion of business loans just to start up businesses and move businesses and stand up businesses in the Phoenix area around TSMC. That's incredible investment.
Mm-hmm. What a bounty. Was there anything you learned? You're familiar with semiconductors, obviously far preceding this trip, but from this trip, did you glean anything just about, because they're in their own gold rush. I mean, we should illustrate for those who maybe don't know, semiconductors now are, it's gold in the 1840s, right? So anything you took away in that space?
It was really interesting to see the coordination between the federal government, industry, and universities in Taiwan. Some of the things that we got to see over there were really familiar. Faculty running research labs, training graduate students, training students that are going to go work at the TSMCs, at the Microns. That felt very familiar. But the science parks, where the federal government sets aside the land, water, and energy to bring together industry with academia to focus on industrial and further down the line problems, around research and discovery that will like help power the global economies of the future. That level of investment and coordination was really inspiring, and something that I think if we replicate here will just amplify opportunity that we've got.
Absolutely. You met Alex Honnold, I believe, hours after his Taipei 101 ascent. Is that correct?
That's right.
Percentage chance he's an alien?
0.
Did you converse with him?
No, I didn't chat with him except for I got in it. Like, there's a really wonderful breakfast like set of buffets at the Grand Hyatt Taipei.
Okay.
And he and his team were clearly staying there because it's right next to Taipei 101. So of course, everyone like on the Netflix team is staying over there. And so I was getting some granola and some yogurt, and he had set down his granola like where I was making my breakfast, and so I got in his way, and like we did one of those little dances where he's trying to go around me, and got exactly in his way, and we make eye contact, and I was like, oh, holy shit, strong work. And then later I asked him for a selfie, and that was all we interacted around.
That's what I got, was a selfie. And I was thinking, like, who needs an autograph when you can get like a chalky handprint, you know? That's perfect. Did you know ahead of time, or did you just see like a mass of people and wonder what in the world?
I saw the New York Times article that had come out a week before around his planned climb, and I forwarded it to my dean, and I was like, Alex is going to be climbing Taipei 101, which is kitty corner from our hotel. And I had the dates wrong. I thought that like it was going to be when we were there, but it was actually it happened when we were on the plane. So I was really sad that we didn't get to see it live.
Sure.
We missed it by 24 hours. But he was in the hotel the next morning, so I got to high five briefly and get the selfie.
Too cool.
And I'm I wouldn't say super fan, but I've gone down the rabbit hole of Wikipedia and YouTube with a lot of Alex Honnold content. So at least I was a medium fan who got to bask in that glow briefly.
Yeah. What icing on a cake of a trip. I mean, to cross paths with a true one of one. I mean, let's make no mistake what he's up to. That's why my alien question was a mere fraction of a joke. Even just now his assortment of interviews, and you just realize, but it's almost like his pulse is, no matter what he's doing, is so low, and that's what I think I'm most struck by. Just how calm, cool, and collected the guy is. Very cool. Well, I'm glad Taiwan treated you so well. Dr. Jankowski, I want to pivot to simulations and digital twins. Obviously, what first captivated me was revisiting your presence on the digital twin panel at Archon. And on this panel, you said something that really, really struck me. Engineering today without computational tools would be like trying to do science without calculus a century ago. In as much detail as you please, how have simulations, digital twins, and computational tools become vital to material science and engineering?
Yeah. So at the core of material science is understanding how the arrangement of building blocks, whether they're atoms or molecules or collections of molecules, how the arrangement of things, how the structure of a material, how that structure determines the properties of the material, how we can process a material. So rolling steel versus pulling steel wire, it gives different structure that gives us different properties. Material science is all about understanding how we can control the processing parameters to get the structure that we want so that we have the performance in the areas where we're going to be using these materials. And so structure-property relationships, understanding how the building blocks are arranged and how that determines the electrical conductivity, the stiffness, the strength of a material is foundational to a lot of modern society. Computer simulations give insight into how things like thermodynamics drive the assembly of atoms. So if you take a pot of water and you heat it up, you change the temperature of the water, and the properties of that water change as a function of temperature. And if you make it hot enough, it starts to boil, and something becomes 4,000 times less dense all of a sudden, just because you've added heat. And that's one way that we can process water. that structure of water in the vapor, or the structure of the water in the liquid, or the structure of the water in the solid phase are really different structures that have very different properties. And it's this sort of playing with recipes, playing with the conditions of materials that we do as material scientists to try to make the computer chips that perform the logic of deep neural nets, or store memory, or the wings of aircraft that are both efficient to manufacture and light enough to lower the energy footprint of flying, and strong enough so that they never fall off of the plane. The doors falling off the plane, that's mechanical engineering. That's not our problem. So computer simulations give us a way to predict, given a set of ingredients and the conditions that those ingredients are sitting in, a temperature, a pressure, a number of molecules, it gives us the ability to predict what is the thermodynamically stable structure. And then we can go from that structure and ask, all right, what's the mechanical strength? What's the electrical conductivity? And how might that impact the performance of this material in a bunch of different situations?
Okay, a quick rewind. The wings of a Boeing 787 not falling off versus the doors, but you said mechanical engineering. More clarity, please.
That's just a dig at our friends down the hall. So much engineering is inherently interdisciplinary now, where the boundaries between mechanical engineering and electrical engineering and biomedical engineering and computer science are really blurred. And so it's really unfair to say that the doors falling off the plane are mechanical engineering's fault. But that's something that's been in the news lately. And Boeing, when they make the 787 Dreamliner, the wings of that plane are plastic. It's a carbon fiber composite. And you can see them flex in a way that the aluminum wings on previous generations of aircraft don't flex. And that's a good thing. And also, those wings are super over-engineered. There's way more material than there needs to be so that the probability of failure is so infinitesimally low, because Boeing as a company wouldn't be able to survive the wings falling off of a plane that have never fallen off before, right? That's some fun insider information around the material science about those wings. But it points to the opportunity that exists in improving technologies that we kind of take for granted today. The job of the material scientist is to understand what is the structure of the epoxy matrix that holds together those carbon fibers so that it is strong enough, and is drilling holes in that going to create places where stresses concentrate and cracks propagate from? Or can we make new kinds of wings, kinds of joints with the fuselage that don't require drilling holes, that take advantage of new technologies? Those are things that we work on with our simulations.
And that just sounds like, if we're talking strictly advancement, is that just raw experimentation that leads us to these voila moments that can actually make something, even though you mentioned it's an infinitesimally small chance that something does go awry, that we can make something, whether it's more efficiently and that's what these simulations do aid? Is this?
Simulations can be used in a bunch of different contexts. Sometimes we've got a technology that we understand well and we're trying to optimize it. So in that case, you might think of the simulations that are used in Formula One, where we're looking at how does a teeny tiny change to the geometry of a wing affect airflow? How does that affect grip? How does that affect drag? How does that affect overall fuel efficiency? So that's one area where simulations are super, super useful. Another place is understanding what are the rules that we're working with for something that's totally new. So I talked about bonding a wing to a plane without fasteners. This is something that we've worked on, that we had a project funded on by NASA in collaboration with University of South Carolina and Mississippi State. This is a collaboration that we had with University of Southern Mississippi and University of South Carolina, where we were looking at a kind of material called thermoplastic based composites. So in the 787 wings, that's a thermoset composite. You take epoxies and amines, it's just like the epoxies that you buy at Home Depot. It's that tube of two things you mix together. It gets hot, then it gets hard, and you use it to make carbon fiber boats. The carbon fibers that are in the wing of the aircraft are held together by this composite that allows the stresses to be distributed across those very, very strong fibers. So you get something that's both strong and light and doesn't fall apart. So thermoset composites are the opposite. You heat them up and they get softer. Thermosets get hard when you heat them up. Thermoplastics get soft when you heat them up. So they've got a maximum operating temperature where they'll melt above that. That's not good. But if that operating temperature is high enough so that we can get these materials to stick together, and what's happening at the teeny tiny nanoscale level is really cool. It's like nanoscale Velcro. So you can take two thermoplastic pieces, butt them up together, heat them locally, and you can do that heating by vibrating it, by sonicating it, by using an induction coil. There's a bunch of different ways to heat it up locally. But those polymers locally will start to entangle with each other. And once they get knotted up enough at that interface is as strong as the bulk material on either side. And so we can, in principle, make lots and lots of small parts, throw away the defects, and only weld together the parts that are compliant to build larger structures from these small building blocks. This is important for today's aerospace manufacturing industries because if you're making drones, the blades on those drones, for example, or the fuselages of like small urban air mobility vehicles, they've got complicated shapes. You're trying to make tens of thousands of these a year instead of like a couple of dozen from the Boeing 787 perspective. And so it's a different manufacturing paradigm that you're working with. And you need to be able to make lots of things quickly. And for a 787, you can't, right now you have to bake the parts in an airplane-size oven to set that thermoset. Those are slow, expensive, and if something goes wrong, you have to start over. Just like if something goes wrong with your cake, you have to start the recipe over. Whereas if you've got lots of small parts, each of those things is a relatively low overhead to make, and you can do them in parallel quickly and put together the smaller parts that have passed quality control. So if you're doing this, if you're making aircraft from parts that are bonded together, now we need to have rules around how strong is strong enough to like certify a part, a wing, fuselage is made from all of these different building blocks. So we need to understand what's the physics that's going on when we're bonding these things together. This is where our simulations help, is to be able to predict, okay, if the amount of entanglement between two parts is above this threshold, we expect the strength will be high enough. And that's something that we can make predictions about in our simulations. We can go do those experiments with different chemistries at different temperatures to validate whether our predictions were correct. And if they are, that tells us that we have some understanding of what's happening under the hood molecularly. And if those predictions don't line up, then that tells us we don't know what's going on over here and we need to study some more. And so it's been really fun to participate in panels with the FAA and with folks from Collins Aerospace and Joby Aerospace and Boeing to try to have conversations around what does certifying parts and inspecting parts need to look like for these new carbon fiber thermoplastic-based technologies that are starting to take a bigger position on the global aerospace landscape.
Certainly. Wow. What a trajectory. And if you to be just in the throes of it, that's a superb illustration of the detail I was really curious about. So thank you. We have extensive ground to cover that I'm very curious about. And I thought to inform the conversation that's ahead, I wanted to just get a breakdown, because you're not a jack of many trades, you're a savant of many trades. Your average day, Eric, so between administration, curriculum, you are a professor, so instruction, and then doing the science. On average, how do your days break down? Let's go on a weekly basis.
Okay. So a pretty normal day, I'll wake up around 6, eat breakfast, bike to campus, start making coffee on campus around 7:30, and have conversations with the faculty, students, and staff that are around the coffee making area.
Okay.
And I really look at that as part of my administrative responsibilities as the director of the Micron School of Materials Science and Engineering. My responsibilities are to make sure that our curriculum meets the training needs of the industries that we support, that our curricula and our faculty are serving students, so that we're being responsible in training critical thinkers that can go into a variety of jobs and get up to speed quickly and serve the public good efficiently and also get paid. Understanding how our students are experiencing our courses on a semester to semester, a week by week basis is part of my job.
Yeah.
Understanding how our faculty are navigating the funding landscapes, the interactions across each other, the interactions across the university is also part of my job. The universities are self-governing things. So faculty are administrators, we're teachers, we're researchers, we're the policymakers, we're the policy enforcers. And so if we want to change the rules, we need to try to efficiently have those conversations to say what we value and how we'll follow up on those values.
You mentioned training needs of these industries that you'll eventually feed with young adults. Mm-hmm. What about staying abreast of that? I mean, how volatile and unpredictable are those training needs? How much does that shift, and how do you stay abreast of them?
That's a really good question. Engineering jobs fundamentally require some competencies with domain-specific kinds of knowledge. So like if you're working at Micron, you need some understanding of how ions implant into silicon to understand the business that we're working with. And similarly, if you're working at Boeing and you're working on thermoplastics, you need to understand what a thermoplastic is. So some background in the fundamental physics, the fundamental science that underpins one's business, that's something that'll never go away. And something where we're adding more knowledge and figuring out what to focus on is always a challenge, but that's sort of a easy, relatively easy choice to make in the sense of whether we focus on aluminum wings or carbon fiber wings, having a fundamental understanding of materials and wings is a foundation from which a critical thinker and a lifelong learner can build additional knowledge. The part that's a little bit trickier is managing industry-specific demands with the constraints of our curriculum and fundamentally new technologies. So like calculators were a new technology that changed engineering education. Slide rules were before that. AI is another one right now. In between there, I think we actually haven't even caught up yet in using computing, programming, and simulations, integrating that into curricula in the way that I think many simulation-focused researchers would have liked to see more broadly. And so the recent push to incorporate large language models into curricula and incorporating large language models into the work that we do, I think for many simulators are like, well, you've already not taken our advice around the things that we could do with more well-developed computational literacies. Now the set of things that we already can't fit into our curriculum is so overflowing that it's freeing in a way where we can take a step back and think about the durable skills around technical communication, being able to think critically. And I think today, one way of framing AI education, which I'm going to kind of be pedantic about specifying as today, when people say AI, they mostly mean applying large language models, which to many technical problems aren't super useful. What was I going to say here? I think that that like one of the things that this kind of furor around the changes that are possible with AI tools and large language models is highlighting that the ability to very agilely learn new skills and figure out like what one needs to learn to be effective with computational tools or tools in general in a new discipline, working at the interfaces between different disciplines. I think that's something that will be a durable set of skills that serves engineers for many decades.
We covered extensively administrative and curriculum-related tasks and focuses. Your teaching schedule and your lab time, how is that divvied up, and when and how?
So faculty have a technical like workload distribution. On paper, I think right now I'm supposed to spend 60% of my time, or something like 50% of my time on my administrative duties, 20% of my time on teaching duties, and 30% of my time on research duties.
Okay.
And so like 20% of my time you can think about as being like 1 day a week. So like 1 day a week is the amount of time that I've allotted to teaching. And teaching it, that's kind of objectively hilarious. Teaching is like a vapor. It will fill up as much space as you give it. And if you've got a classroom with 180 students that are interested in material science, but not all material science majors, 180 students is a ton of different conversations to have around how to connect your interests to this discipline and whether or not it makes sense to dive deep and focus and get a job as a material scientist, or to incorporate content from this degree program in a minor to supplement your career as an accountant for a semiconductor company, for example, or to go running in a different direction and say, okay, I appreciate what's happening over there, but that's not for me. That's cool too. But it is laughable to think that I can have the same quality time with all those students when there's 180 of them versus like 12 in a smaller graduate like simulation class that I might offer in a different semester. Both of those semesters, I get to allocate 20% of my time, 1 day a week, to do those things, which could take all 5 days of that week. So, and we can kind of apply that same sort of hilarity to the research side of things. That 30% a week, so a day and a half, is the time I should be allocating towards writing research proposals, writing papers, responding to the reviews for those papers and for those proposals, managing those funded awards and the graduate students that they fund and the infrastructure that we can buy with that. So like that involves running a small business, like doing purchasing, the logistics of taking deliveries on things and unpacking a new piece of equipment and making sure that you can hook it up to the infrastructure that we've built on campus with like whatever, like the nitrogen and the fume hoods and the electricity and like the three-phase requirements for this particular new device. And in our case, in material science, sometimes that's also like building a special floor that doesn't shake as much, so that this microscope can tolerate traffic going by outside, because otherwise it would be very sensitive to if somebody's parking at the wrong time. I think that from semester to semester, different faculty, myself included, will scale up and back how much they're multitasking versus how much they're really focusing on something to try to get all of these things done. There's days when in class we're talking about something that I'm super duper familiar with, and I have the luxury of being able to walk into that classroom and have a discussion like this where I don't need very much preparation time because it's been built into all of the expertise that I've built over the years. And there's other times when writing a paper on something new will require a ton of focus. And I might spend a week of really dedicated time with my students when the teaching and administrative responsibilities are relatively quiet, and we crank out this paper and send it off to review, and then that's churning in the background while we can, I call it focusing the laser. The job responsibilities require multitasking, but that's not very efficient to try to do multiple things at once. And so focusing the laser on what can I work on right now for 2, 3, 4 hours so that it's off my plate for a while and I can focus the laser on something else. And that's continuously a struggle. One of my staff blew my mind yesterday. She was like, Eric, you're the first manager that I've worked under that for whom managing wasn't their sole responsibility. And it occurred to me that in a self-governing institution like a university, that is the norm. It's necessarily the norm that people wear multiple hats. But it sure sounded like a luxury to have a job where you only had to focus on one thing, managing people.
Certainly. I'd like to point the laser for a brief moment at the CME lab, Computational Materials and Engineering, right?
Yeah.
So the research lab. If you can speak to this, just the nitty gritty, hardware and software. We talked aerospace, thermoplastics. We've talked a lot about stuff. What are we dealing with? The full stack, as it were, in the lab. Take us through it if you'd be so kind.
So the students on a day-to-day basis, we're working at some combination of Linux machines and iMacs and MacBook Pros are the fingers on the keyboard machines that we're working with. We write software in mostly Python, C, C++, and CUDA when we need more performant code. And that code is written for and compiled for hardware that we've got on supercomputing clusters that are both small and large. Some of them are local machines. So we've got, I think, a 14-node Linux cluster that has 2 to 4 NVIDIA V100 or P100 GPUs. So kind of old GPUs at this point. But those V100s are a really great return on investment. So I could spend maybe 30 times more on an H100 today and get twice as much performance. So from a flops per dollar perspective, that V100 is still crazy good. And they're on sale on eBay. So I pick them up when I see a cheap one.
Don't fix what ain't broken.
Yeah. And also, I don't know if this is may come off as like a first world problem, but the push for more AI and machine learning capabilities in modern GPUs has dialed back precision. And so the double precision flops that we could get from a V100 GPU are now not the same with the H100 and A100 architectures that are looking at 16-bit and 8-bit precision for some of the deep neural net backpropagation numerics that don't require double precision floating points anymore. So for some kinds of the calculations that we do, double precision is important. For some kinds, we can get away with single precision. And in other cases, for doing artificial neural net backpropagation, having 8 bits per memory variable is totally fine. So it's been interesting to see the breadth of different flavors of architecture, but for the stuff that we're doing, it's a lot of computations where doing the same operation on multiple pieces of data in parallel are the sorts of algorithms that we're dealing with on a day-to-day basis. So calculating the forces between all of the atoms in one of these polymer simulations, every atom has a bunch of neighbors, and we need to sum up those forces on a specific neighbor, and we need to do that for every particle. So in all of those cases, we're looping over a set of neighbors and adding up forces, and then using those forces to change velocities, using velocities to change positions, and then we do that again and again and again. So the architecture of a GPU is really great for that. And when they first came out, when you first were able to program a GPU using CUDA back in 2006, we were able to do the same simulation that it would take $100,000 worth of CPU architecture in like a $1,000 GPU and like small machine setup. And so that like really democratized the kinds of simulations you could do, and it changed the science we could do. Because instead of running one simulation for a year, now we can do 100 simulations over the course of a week and answer way different questions for the same energy footprint. And that's why we're able to chip away at combinatoric and screening questions like what are the right chemistries and what are the right temperatures for processing this particular polymer to make it as strong as possible or as soft as possible for this particular application.
I'm so curious, if you'll forgive the novice question. We've just dissected just how robust these computational systems are, what's working for you all. Again, the novice, to what extent is just a basic understanding of advanced mathematics essential to material science? Do students have to, because all the computers can do, is the answer none? Or
that's a really good question. And I think one that's, we're struggling to answer right now. So in our electrical properties class, for example, the properties of materials that depend upon electrons depends upon some knowledge of quantum mechanics. Electrons are quantum mechanical particles, waves, both, neither. It's annoying.
Where's that theory of everything? Yeah.
And so some calculus, some linear algebra are the math topics that are necessary to unpack the sufficient quantum mechanics to understand wave functions and how that correlates to different electrical properties. But how much that's used on a day-to-day basis, I think, depends upon whether one is doing fundamental research where manipulating those equations and poking at that math is part of advancing knowledge versus whether it's background information that's important for keeping a machine alive that's pumping out chips. There, that math, I think, is important to have seen once, but you're not using it on a day-to-day basis. There, something like statistical process control and being able to understand and pin down where in a 16,000 step pipeline is the defect being introduced and how do we do the forensics of figuring that out. That's a different kind of math that's also important for a different job that a material scientist can also get.
Utterly fascinating. So not to get too semantic, and I know this particular term is a little more prevalent on our side of the aisle than yours, but when people hear digital twin, they often think it's a building, machine. We just call it simulation for the sake, but in your work, in your curriculum, studies and research, is the digital twin / simulation, pick your term, is it an object? Is it a behavior? Is it a reaction? Is it all the above and it varies?
I think it's a lot of different things. So digital twins are certainly augmented or virtual reality representations of a room that a student might explore to become familiar with where the chemicals are and different pieces are to a microscope that one of our trainees might use to do atomic force microscopy or scanning electron microscopy. It's expensive to make a mistake on a transmission electron microscope. So like using a digital twin to train for that space so that we minimize mistakes is one kind of digital twin that exists in our space. Finite element simulations are another kind of digital twin that's, I think, numerically distinct from the atomic simulations that my lab focuses on, which are numerically distinct from the wave function and orbital-based calculations that density functional theory, digital twins of atoms and electrons, focus their time and effort on. So there's a whole bunch of different flavors of digital twins that exist across our research, that exist across the umbrella of material science and engineering. And I think they're all valid. I think that they're all useful, and you can get a PhD in just one of those and never really scratch the surface for many dozens more.
What's a recent simulation that really surprised you?
I got at least one answer. Let's see. I'm training a bunch of new undergrads on our simulation techniques, and there's this cool phenomenon where the name of the phenomenon is entropy-driven aggregation. So you can take some big, milk. Milk is an example of a colloid where you've got fat and protein globules that are stabilized in water. And these globules are a whole bunch of different sizes, and because they're a whole bunch of different sizes that overlap with visible light, the 400 nanometer blobs and the 600 nanometer blobs and the 800 nanometer blobs, they all scatter different wavelengths of light, and that's why milk is white. But it's because all of the different wavelengths of light are scattered. So in principle, as an aside, if you made milk of only like 500 nanometer globules, it would be whatever color that corresponds to. I don't know if that's like greenish or something yellowish, but you could make like green milk and it would taste like milk, but it would look neon green. That's something that you could do. Anyway, with a colloidal suspension like milk, you can sprinkle in a little bit of polymers that are smaller than the globs. So if the globs are 500 nanometers across, if you sprinkle in polymers that are like, say 50 nanometers across, at the right concentration, all of the globs will stick together and like drop out of solution. And that entropy-driven aggregation comes about from there being more ways for the system to arrange itself with the globs stuck together, because it gives more room to the polymers for flopping around. And that matters more in this particular situation than the globs being separated. So I've got some simulations running where I'm training students to run simulations to find the conditions where this entropy-driven maximization will happen. And this is something that happens all of the time, like happens in butter churning, it happens in paint separating, entropy-driven aggregation pops up everywhere. It's why the Brazil nuts float to the top of your can of mixed nuts. And my students have not been able to find conditions where we see this aggregation. And so that has surprised me in a bad way, that we know that this is possible, and my students are saying, Eric, it's not possible. And this is a great learning opportunity. This is why we do this. Yeah. But that result did surprise me because I know it's possible, and my students are saying it's not. And so we're gonna learn some things there, and I'm proud of the work that they're doing and the approach that they're taking, and also that result surprised me. Let's see, maybe a surprise in a different direction. I
have to ask this, and I'll let you get back to pondering. What was the duration of this attempted simulation to find?
About a couple hours. It's not long.
And just nada, though. Wow.
These sorts of simulations are easy once you know what to do, and extremely difficult if you don't yet have all of the pieces of knowledge. Actually, climbing Taipei 101, I think, is a really great analogy for this.
Ever fitting.
When you hear Alex talk about it, he's like, it's not a technically difficult climb. It is a muscly climb, but he wasn't worried at all. Like, I'm not worried at all about sitting down and running a simulation where we can demonstrate this entropy-driven aggregation. But my students who haven't put in the time with the thermodynamics, who haven't put in the time with the software development practices, that are still new in reading the literature, so that they don't know what concentrations we should be looking at for the polymer and the shapes ratios for the polymer versus the colloids. All of those things matter for being able to see this thing or not. And so it's really easy to fall off the building if you just walk off the street. But with decades of practice, it's not so bad. It's not so bad. Some of these simulations, you might not see the effect if you don't run it for long enough. And so it's possible that my students were looking at the right place and didn't run long enough. But also, when you're learning these techniques, the feedback loop for understanding if you're working in the right way or working in the right direction needs to be tight. If you run a simulation and it takes a week to get the answer to see if you were right or wrong, or if your hypothesis was true or confirmed or not, that feedback loop is too long. You only have a week to try something out and learn something new. The reason that AlphaGo is good at Go is because it was able to play itself billions and billions and billions of times, many lifetimes of humans worth of training to be able to do the pattern recognition that it does. And so tightening that feedback loop so students can learn quickly is, I think, a responsibility. And so I think it's fine that they didn't find it in an hour's worth of simulation, because it only took an hour. And now we can run some more simulations and learn some more from that. That's why we're doing this at a university.
The opportunity cost was not so grave.
Yeah. I think, there is some simulations that I ran as a postdoc when I was at CU Boulder, where we really simplified one representation of a molecule. So instead of all of its atomistic degrees of freedom, we broke it down into what we thought were the most important constituent parts. And this enabled us, in some ways it's kind of cheating. We're abstracting away a bunch of detail that really matters for how these things work. On the other hand, it allows us to overcome some barriers to inquiry in terms of performance that were in our way. And we were able to, these simulations ran quickly, and we were able to see structures emerging that we know were observed in experiments. And so these simulations where we were able to, I'm going to use the word cheat, but not in a bad way, where we were able to identify the fundamental physics that really mattered here. In identifying that set of fundamental physics, we were able to show that this physics is what mattered most for the structures that emerge from thermodynamic molecular self-assembly. And it was easier than trying to include all of the detail and making sure every little bit was right. And that surprise was so wonderful to see how we could be more efficient and make more discoveries while making our lives easier. That was a wonderful surprise to see back in 2012.
Terrific story. Wow. Not letting perfect be the enemy of good. We've talked at length about aerospace. I'm curious, where else in material simulation does approximation perhaps become dangerous rather than useful?
Well, I think at every scale we're approximating. So when scientists talk about scale, they often are referring to length scale. So at the tens of nanometers level is like one length scale that matters for semiconductor circuits. At the slightly smaller length scales, we were talking about individual atoms. Slightly smaller than that, we're talking about subatomic particles. And so when a theorist is doing calculations about wave functions to predict the electronic structure of a crystal, like how adding boron to silicon is going to change its electronic properties, these are calculations that we can do with first principles calculations. And those are approximations. We separate the how the wave functions of the nuclei are connected to the wave functions of the electrons, and that's an approximation of reality. When we pretend that atoms are billiard balls that bounce off of each other, that's an even larger scale approximation of what's happening under the hood. When we use a finite element model to represent a material as a beam that has uniform thickness and uniform Young's modulus across the entire beam, that's an approximation of reality. At every single scale, we make trade-offs between the amount of physical detail that matters and the resolution and the accuracy of the calculations that we're making. And I think that actually understanding those trade-offs is maybe fundamentally what we're doing when we're training engineers, is providing some intuition around how many decimals of precision do I need to say that Ellis won't die on this flight with maximal certainty. Where is two significant figures sufficient, and where is that dangerous? I think under the hood, that's what we're doing, is making sure things are safe using math and the physics for how things work.
Zooming out from the CME lab, I'm curious, the notion of one being stuck in one's ways and material science at large, to what extent is there a problem, if one at all, about resisting emerging technology and innovation and computation? And it's just some modern fad, or does this exist in the quote unquote community?
Sure. When I was at postdoc at CU Boulder, my advisor there was working with a number of colleagues that expressed verbally the opinion that simulations weren't real science. And that was extremely hard for my mentor there. I think that certainly today there's a lot of skepticism and pushback, deservedly so, around large language model hype. There's lots of great artificial intelligence and machine learning applications of computing power, and certainly there's a lot of hype that has yet to deliver on the amount of capital investment and energy investment that we're putting into growing the ability to train larger and larger language models. I joke a little bit that material science and engineering is it's materials science, which is discovering truths about matter and the universe and how the world works, and engineering, which is exploiting those truths for profit. And the science part is requires skepticism, and so fundamentally being skeptical about the promises that some new thing has is healthy. It's good. And changing one's mind when those skepticisms have been disproven is also a responsibility. And so this one step forward, two steps back, or two steps forward, one step back, that dance is a requirement of scientific inquiry.
It's the year 2040. What's the dream state of material simulation?
So
this can be for you.
Yeah.
Personally.
So there are some parts of molecular simulation, of materials simulation, that I call computational bullshit. Like it's, needing to understand very deeply, like the Linux operating system and the different flags that you might pass to the top or head commands to parse textual information to make a simulation go. And it occurs to me that like those don't super duper matter to the fundamental physics and understanding of the world. They're kind of computational bullshit that we have to swallow en route to running high performance simulations of different materials. And also, they are the reality on which these supercomputers are built. And so being completely ignorant of them, I think, would not allow us to fix problems in a future where we need to reinstall the operating system and start over from scratch with running a job. So I don't know, I think, let's see, 2040, that is 14 years away. It would be lovely to be able to express in words the question one wants to answer around simulation of a polymer and be able to spool off the hundreds of thousands of jobs that are necessary to do this on the right architecture and have those results come back and be able to sift through them to gain some understanding of how polyether ether ketone or polyether ketone ketone can be processed in monodisperse or polydisperse mixtures to get the wing that we need. But to do that requires a lot of really behind the scenes important grunt work that's that requires being able to manage the data provenance of all of these different jobs across distributed clusters on the planet, and pulling that information back and being able to parse it and search it and organize it, and that's database programming. It's it's kind of boring. It's not super sexy, and If we solve all of the boring problems that are behind the scenes, that would make molecular simulations way better. And it's something that our team is working on a little bit. We've got a grant from the National Science Foundation working on building computational infrastructure for polymers specifically to help with some of these specific things. So if that grant is successful and if the spin-offs from that are successful, maybe in 2040 we'll be able to say in words, I want to know what is the optimal chemistry to make the next generation of drones from and what temperatures to process it at so that I can minimize my waste and maximize my throughput. Being able to spool off the simulations that are necessary to answer that question and be able to interrogate and be skeptical about that information and have it checked by a number of experts, that would be super cool.
And ostensibly, it seems fairly plausible. I'm going to say from the total novice's chair, I would imagine just with this influx of data management capabilities and just how nascent we are already with just LLMs and everything, I'll hold out hope. Okay, Eric, I'd love to pivot to some partnerships and case study talks. We explored the NASA one earlier, I think. Can you detail your work with the Idaho National Laboratory?
Yeah. I guess I can answer that in sort of two different ways. One is the projects I've been involved with at Idaho National Lab, and one is collaborations that Boise State and the Micron School of Materials Science and Engineering has had with Idaho National Lab. INL is one of the technology hubs for nuclear technologies. They also do a lot of work with broad energy-related technologies. around batteries, the different materials that are needed in batteries, wind, solar, water purification, lots of really great science is happening over at Idaho National Lab. And some of our faculty, Brian Jaquist in particular, also Mike Hurley and Dave Estrada, many of our faculty are involved with different questions that overlap with nuclear technology. So Brian Jaquist is an expert on uranium nitride fuels. He works on the cladding materials, the steel alloys that we use to hold the pellets of nuclear fuels inside of a nuclear reactor. Mike Hurley is an expert on corrosion, making sure that those steel tubes don't rust and burst open, and how that science can help us minimize the degradation of everything in our built environment. So rebar corrosion is a huge deal that overlaps with nuclear fuel science. Dave Estrada and Mike do a lot of work with advanced manufacturing, so figuring out how to print steels with 3D printers and make electronics from inks that allow us to print semiconductor materials or printed flexible electronics. Those overlap between the science that we've done at Idaho National Lab and other biomedical technologies that Dave Estrada's lab is working on. And so I got first involved with Idaho National Lab, helping to do simulations of nanoparticle sintering to develop better sensors for the nuclear fuel piles in a reactor. So you can't run wires and have a thermocouple in a nuclear reactor because you've got all of these neutrons flying around that ruin all the electronics. So like, how do we get information about the temperature of those uranium pellets out of the reactor without indirectly inferring it from like the temperature of the water? That's a difficult problem. So we were working on printing strain gauges that would change shape or change other electronic properties, like or even like acoustically, like pop and like crackle and snap and make noises when they're changing temperatures. So we were doing some simulations for this big initiative with Idaho National Lab to help develop better temperature sensors for nuclear reactors. It was one of the first big projects that I was involved with as a young simulator at Boise State, and that was a great partnership. They've also got other funding opportunities called laboratory directed research and development funds. These are internal grants that scientists at Idaho National Lab will apply for internally to spool off high-risk, high-reward projects, often that have a focus on collaborating with nearby universities. So they've been a great opportunity to get involved with different surface science, so like catalysis or electrolyte materials for batteries. We've had some projects with INL on those materials. And a lot of our alumni go to Idaho National Lab either as interns during their training or for full-time employment afterwards. So we've got a rich history and a long connection with INL that's been great from the material science perspective.
That's beautiful. Micron and other semiconductor victories.
Yeah. About 30% of our graduates go into the semiconductor industry, whether that's Micron or ASML. So I'm going to rattle off a few names. To make memory requires a whole bunch of infrastructure. It requires making masks. So these are basically transparencies that prevent light from hitting parts of the chip or that focus light on certain parts of the chip to draw lines or to scratch away material where we want it or don't want it when we're building up the circuitry infrastructure for logic or a memory chip. And a company like Photronics, their whole business operation is doing the manufacturing of the masks that are used to block extreme ultraviolet light, which is a fancy word for X-rays, to focus X-rays onto silicon and to strip away photomask from the chips that are being made by TSMC or Micron. Companies like ASML, they make the giant machine that one of costs $400 million and uses Photronics' masks inside of it to draw these lines on these chips. The wafers that are being shined with this ultraviolet light, they experience 5 Gs of acceleration coming in and coming out of this device while being shined with this light that's generated by shooting droplets of tin with a laser 10,000 times a second. Like, it is the craziest.
It sounds farcical. I think I've read that ASML, correct me if I'm wrong, that they are actually a literal one of one. I don't think any company does quite what. Maybe I'm wrong on that. No, DJ, let's cut that.
ASML is the only company that makes this ultra high, the extreme ultraviolet patterning machine. And so they make one product, they sell it at $400 million a pop to the Microns, to the TSMCs, to the chip manufacturers around the world. And the story behind that is really fascinating. And the places that it could have gone wrong, and the investment and ingenuity of all of the different parts of making that company go is really, really super cool. Mm-hmm. Companies like Applied Materials are also suppliers for the semiconductor industry. So all of these different companies are potential employers that have a really tight relationship with the TSMCs, with the Microns, with the Intels, with the AMDs, with the NVIDIAs, that go from taking designs and turning that into real products that you can buy and put in your computers.
Is it a safe assumption that the meteoric rise in demand for these chips has directly correlated to your lab, your curriculum? I mean, because obviously these chips have been around. You've been in Boise State a decade, 11 years, is it?
Yeah, I've been here 11 years.
I mean, how has it evolved? Has it just been in lockstep with this meteoric rise?
So I should back up a step and mention that, like, the reason that we're called the Micron School of Materials Science and Engineering is Micron has invested millions of dollars into our school and into Boise State University over the past couple of decades. And so we wouldn't be here without that sustained philanthropic investment, which is incredible.
Yep.
And so, I wouldn't say that anything in our curriculum is a direct result of, has a direct through line to any specific technological development, but certainly the work that we do in our labs, the training that we provide our graduates, has played a role in the workforce that has been moving the needle on semiconductor technology developments. We have graduated on the order of 65, 69 PhD students now over the last 14 years. It's not a crazy huge number, and 30% of them go into semiconductors. The other 70% go into aerospace, go into business, go into steel. There's tons and tons of different industries that our graduates go into. And so our researchers that are at the semiconductor companies are often some of the folks that are getting the patents that are part of the technologies that enable to make something a little bit smaller or go into the third dimension instead of staying 2D. So there's definitely contributions, but this is contributions from hundreds and thousands of people from many thousands of universities worldwide that's making all of this stuff go, which is really an incredible thing to both be a part of and recognize that, we do have some, maybe outsized influence relative to the population of Idaho, which is pretty cool.
Most certainly. I wanted to double click on something mentioned earlier. Mm-hmm. Maybe my homework was wrong. I thought you landed the NSF grant, National Science Foundation grant. Was I? We've landed a few. And I think the one that you're talking about is the AWESOME Center. So Advancing Workforce Experience in Semiconductors through Outreach and Mentoring Excellence.
And I think this is probably a great opportunity to disambiguate like what that is and my involvement in it.
Swell.
So this center is a $7.5 million center for research and what does CREST stand for? Center for Research and Center for Research Excellence in Science and Technology. CREST. I think that's right.
That'll suffice.
It's close to that, if it's not that exactly. And so this is a $7.5 million center funded for 5 years by the National Science Foundation. And what these centers are the ability to pull together multiple labs and educational infrastructure in a way that's greater than the sum of its parts. So I am the principal investigator on this grant, but the 4 central labs that are at the core of the scientific developments of this center are run by different professors who aren't me. So those 4 professors are Lon Lee in Materials Science and Engineering, Elton Gronyard in Materials Science and Engineering, Karthik Srinivasan in Electrical and Computer Engineering, and Curtis Cantley in Electrical and Computer Engineering. And these 4 labs are incredible. Across those 4 labs, we are developing the technologies that are going to help us lower the power footprint for training things like the large language models of the future. So Lon is doing the density functional theory calculations and the machine learning to identify the right recipes of ferroelectric materials that Elton Gronyard is going to grow with atomic layer deposition. So Elton makes these ovens. They don't look like the ovens that you are familiar with in your kitchen. They're these tubes where we can put gases that will react with surfaces and then purge them and do that over and over and over again to grow up layer by layer the exact stoichiometries that we want, to have the chemical properties that we want, to have the exact structure that we want. It's a really specific processing technique for growing up materials layer by layer. And we think that we can grow these ferroelectric materials using atomic layer deposition and hand those off from Elton's lab to Karthik's lab. And Karthik is an expert on photonic computing. So using light instead of electrons to do the logic of computing, flipping bits in these ferroelectric materials where we can use different wavelengths of light to flip bits in the same spot. So increase the memory density and lower the switching cost of flipping a bit by using light instead of electrons. And if we use these ferroelectric memory elements in spiking neural networks, so doing in hardware the same math that we're currently doing in software on top of GPU architectures, if we do these artificial neural networks in hardware with these ferroelectric memory elements, we think that we can lower the cost of training AI by a factor of 100.
How ambitious.
It's pretty cool.
Wow.
And so these labs are the center of the center. These are the technology advancements that we're trying to link together across these 4 labs. It'll be way bigger than any of the individual labs, just focusing on, ancillary ideas that overlap with this. By focusing these efforts together, we think that we might be able to move the needle on lowering the cost of training AI more than working individually. That's how we've justified this center. And there's a major education element of this in helping the broad Boise State community become involved and understand the awe of this research. So it's called awesome because it is so awe-inspiring to know what it takes to make a chip, to draw these tiny circuit elements line by line and see how they're more complicated than like a city skyline. There's more detail in one of these chips than you can resolve in looking at New York City through a telescope. It's crazy. And helping the broad graduates from Boise State, irrespective of major, get a foot in the door with these labs. So we've got a building on the modern computer course that we're going to call Switch in the fall that any student can take to learn about the history and future of computing, to help provide some vocabulary and some context for participating in these really important decisions that we'll have around building data centers and the usage of water and the usage of energy and how we use our public resources, how we use taxpayer dollars to make decisions that demonstrate our values as society. And so I think that the courses that we're making, the accessibility into these 4 labs and the specific training for the scientists growing in these labs are a really wonderful opportunity at an important time for Boise State and for the Treasure Valley. But I just run the center. So my job is wearing another administrative hat and making sure that coordination happens.
Sure.
Having the broad picture of how this connects with Taiwan, how this connects with Micron, how this connects with the different industries in the area, how we can coordinate with the College of Western Idaho, the College of Southern Idaho to help the students that want to do welding for the piping that goes into the super pure air handling for Micron, make those job connections. And for the students that want to hop off that track and go into the microscopy route, make sure that there's a smooth pathway to come to Boise State and they can finish in 4 years and it doesn't extend the amount of loans they need to take out to finish their education. Those are policy decisions. Those are curricular decisions that as faculty at universities, we have power to improve, and that coordination puzzle is part of why I'm involved.
To come back to what can be described no other way as an awesome grant. How, again, for the layperson, do these come to be made available? What is ground zero for these to happen?
For writing and landing one of these
grants
national...
being made available, accepting application submissions, I don't know what you would call them. Are you notified? Do you get an email? From the NSF?
You get an email from the NSF when you've been selected. So,
well, I'm talking about so you've been selected, not to apply, but I'm talking about, there's this new grant being made available that's just issued.
Yeah.
You get that email?
Kind of. So the National Science Foundation has a number of email lists that you can get on to get updates from the geosciences programs or the material science programs or the mathematics and physical sciences programs. So you can get on these different email lists. There's also people at the university whose job it is to have their finger on this national funding pulse. So our the vice president of research at Boise State, Nancy Glenn, does an amazing job of coordinating, understanding what funding mechanisms are available. That's the terminology that we use as researchers. There's what funding mechanisms are available through the Department of Energy, through the National Science Foundation, through the Department of Education.
Okay.
Are we, as an institution, competitive for these different funding mechanisms? So which ones should we prioritize? And as researchers, you often have a very specific idea of the sorts of funding mechanisms that you're competitive for. So I apply for those through the National Science Foundation, through computing related opportunities, through materials related opportunities. There's some polymer specific related opportunities. So anything that overlaps with those are the ones that I pay attention to. But the ones that are around geosciences, even though they might be doing the same math as us, or applying computing to understand weather patterns or ocean currents, some of that math might be similar to what we do, but it's a totally different application area where it doesn't really register on my radar. Even though I high five the people that are working on that. It's super cool. So sometimes I will find out about a solicitation. That's the vocabulary term for the website that says when the deadline is, who's eligible, what you need to submit to apply to the solicitation. And then there's always a link to the proposal, acceptance, and preparation guide. It's this 270-page document of rules for the National Science Foundation. And there's different rules there's rules that exist around being able to accept a contract with the National Science Foundation, the oversight around auditing and spending that's required to be able to receive one of these grants. And so institutions of higher education, nonprofits, are typically who is eligible to apply to the NSF grants. But there's also funding mechanisms for small businesses. So these SBIR and STTR funding mechanisms are specifically for translating technology into small businesses that take the discoveries that happen in our labs and make them into economic drivers and products and services that can impact society today. And that's an important part of the overall funding portfolio. So we find out about these different funding mechanisms. We make the decision about whether we are ready to apply. So for something like a $7.5 million center, this is not, if you've got 6 months between the announcement and the deadline, that is a really short time to get your ducks in a row if you're not already speaking the same language and have the team ready to go to apply for this center. So a lot of the work in getting ready to apply for a giant center grant like this is doing science together in teams and making sure that we can trust one another to deliver on results in high stress, fast moving situations. And so when a solicitation comes up like this one, that was really perfect for Boise State, we were able to pull that team together to shape the vision for what this center would look like and have an umbrella over 4 different labs rather than focusing one lab that maybe 3 other labs would work under. That organizational structure, the reporting structure, the timelines for how we do the work, the evaluation of the scientific parts, the evaluation of the qualitative research that we do about the researchers to see, does bringing story listening techniques into our mentoring plans for the postdocs and the graduate students that are participating in this, does this develop them as professionals better or more efficiently than if we didn't do those things? Mm-hmm. And so like these are large, complicated, the budget for a $7.5 million thing over 5 years is a large and complicated thing. And, a lot of the work that we're doing day to day is getting ready for those next big opportunities so that we can bring in more federal tax dollars to benefit our local economy, to benefit the researchers that are participating in this, to grow the next generation of scientists, and to get those folks out in positions of power, of authority, in making important decisions around how our economies move.
Eric, what a window. I mean, it's really, I'm going to use the word exciting, just into the ecosystem, the partnerships that you've just laid out. I want to close this topic by asking what the deepest satisfaction you felt in your position thus far has been.
It's always hooding students at graduation. It's easy to forget that doing research is fundamentally a human endeavor, and humans are messy, and there's days when our students get hit by a bus. There are days when they're sick. There are days when their loved ones are unwell, and it's never a straight path from showing up for class on the first day and getting your bachelor's degree, and even less of a straight path from showing up on the first day of a PhD and leaving with a doctorate that says you are a professional scientist and you are ready to advance human knowledge. And for all 6 of the PhDs that have come out of my lab and the 65 PhDs that have come out of our school since I arrived, those are all, intensely personal relationships that are different between each of those students and their faculty mentors and the connections that they make across the school. It really is a community of support across the students, between students and faculty, between our staff, students and faculty, that makes our program so special. And knowing the obstacles that our students have overcome and seeing them get that hood to signify their doctorate at graduation, that is always the most satisfying part of this job. It's the best. And we get to do it every semester. Every semester we get to hood more students. It's so good.
Beautifully said. Dr. Jankowski, I'd love to explore material science and engineering through a historic lens.
Okay.
What are 3 watershed moments in the science? And they don't have to be ranked first, second, third, but 3 that come to mind is, whoa, just true red letter days.
So I think figuring out how to extract lead and work it was a discovery that enabled the movement of water for aqueducts and irrigation that was essential to changing the ability to make cities and human society that emerged around city centers. That's a major one.
That's great.
I think gunpowder is kind of a cop-out, but also...
but that's hard to omit. Yeah.
Yeah.
I'll grant that.
Okay.
Yeah.
And if we're restricting ourselves to 3, then I think...
Was that the Chinese? Gunpowder?
Yeah.
Okay.
Right. So like gunpowder allows us to do rocketry. It allows us to make guns. It allows us to wage war in different ways.
I mean, in terms of pure impact, it's hard to...
That's a big one. And I think if we're restricting ourselves to 3, I'm going to have to say figuring out how to make transistors out of silicon to do, to make materials the devices of information manipulation, being able to outsource to rocks. We're taking rocks and we're using rocks to do language, to store memories. That, I think, is a major watershed moment in human history.
Who's the most unsung hero in your field? This could also be a technologist too. You deal with computation. Does not, I should say fields, shouldn't I? Technically, you polymath you.
Most unsung hero. So I actually want to push back on like the, I don't know, like deification of scientific heroes, because none of them did anything in isolation.
Okay, a non-household name that maybe deserves to be.
So like, I also like, this might be an unpopular hot take, but like,
Let's go.
The Nobel Prize maybe does more harm than good. Like we should reward teams of scientists and reward collaboration and collegiality and like helping, not like what technology was the coolest. I think that changes the reward structures.
That's fair.
In unhealthy ways. And, but.
That's very fair.
Let's see. What are some great names that maybe, I mean, like the math of diffraction with Rosalind Franklin and discovering the double helix structure of DNA. That's a good one. Like she was the one behind the scenes with Watson and Crick.
Get all the cred.
Yeah.
There you go. Case in point.
There's a scientist named Lynn Conway who did a ton of work around being able to lay out circuit elements, and I think is a huge unsung hero of modern semiconductors. And Lynn transitioned from male to female in like the 70s. I forget exactly when, but like a long time ago.
Yeah.
And I think really has been a hero for trans rights and voices and activism in a way that's super cool. So Lynn Conway is another, I think, unsung hero of modern semiconductors and materials logic. Yeah.
Look at that. 2 solid answers. Okay. Is there a contentious debate ongoing today in material science?
Lots of them.
Most contentious.
I mean, at the conferences I've been to, I've seen people shout about the structure of water at high pressures.
Oh boy.
That's a contentious area. I think there's contentious areas. Well, I think around.
You know, what about, can I possibly tee you up on one?
Yeah.
I'll say hopefully imminent nature of maybe, interplanetary travel, something along those lines. Anything where this is not possible? Yes, it is. We can.
Well, so, I think there's a lot of contentious science around interplanetary travel. Zach and Kelly Weinersmith are two authors that just wrote a book on colonizing Mars and whether it's a good idea and have we thought things through. It's a well-researched deep dive into sex in space and surviving the trip and terraforming Mars.
Yeah.
And I think those are really clear-headed explorations of, the observations that if we can't even take care of the planet that we've got here, what chance do we have to fix one that's already inhabitable? I think is a great summary of that thought. And we should not give up on big dreams. I think it's wonderful to think through the technologies and the strategies around living on the moon and getting to Mars and getting to Alpha Centauri and finding habitable planets that are within our ability to travel to them and advancing our ability to travel through space faster. I think those are worthwhile pursuits. And also, we should not do that while ignoring urgent problems that we can solve with policy here today. We have a responsibility to take care of the people that are here and build for the future.
What's a common material that most people wouldn't know is a miracle and how we're able to use it?
Fabrics. You take your shirt for granted.
Okay.
Okay. Now think about a cotton T-shirt.
Yeah.
So cotton is a fiber, there's a poofy little poof of fiber.
Yeah.
And to make a cotton shirt, you've got to turn that poofy plant into threads that are of uniform thickness and that are long. How do you make long threads of cotton from a poofy little plant? Then you've got to take those threads and you have to weave them into a fabric that you can then use as the baseline, like these textiles, for putting together shirts and pants. The theft before clothes became an overlooked luxury item were of clothes, like stealing somebody's coat, stealing somebody's tailored pants was the easiest way to transfer wealth from one area to another, because these were hard things to make that took a ton of expertise. And the fact that we've outsourced all of this expertise to looms that are automated, that can churn out lots of fabric in a short amount of time, and have made mechanical all of the labor that used to be done by hand. I think that has made shirts, fabric, materials that are incredible, that people don't think about how just wonderfully complicated the process of making them is. And now there's clothing waste because we produce so much of it so quickly that people don't think about their clothes anymore.
What a parallel with food, by the way. I don't know if that was intentional or not, but wow.
Mm-hmm.
Yep. What's a materials problem that's been almost solved for years but keeps eluding us?
So earlier when I was talking about how thermodynamic self-assembly drives the structure of things like polymers, and we try to exploit that as material scientists and simulators, there's an idea of exploiting thermodynamic self-assembly to make arbitrarily structured materials for whatever applications that we want. And it comes out of observing virus self-assembly. So virus capsids are collections of proteins that in half a microsecond arrange themselves around RNA or DNA, depending upon the type of virus, and do this reliably and reproducibly every time they burst open one of the cells in your body with the copies of themselves, the ingredients to make themselves that are manufactured when you are sick, when you are infected by a virus. And that virus self-assembly was one of the original inspirations for me getting into this research that I do. And so the idea is like, wow, if we can pick the right building blocks, have the right shapes and right interactions, we can make synthetic viruses that deliver drugs to exactly the right places in the body instead of relying on, just a certain concentration being in your bloodstream. Or we could drive magnetic particle that has the right drug to the right place and release it with the flip of a magnetic switch, like in your meniscus, in your knee, after we've guided it there with magnets. So some of those things we have made advances on, and we've better understood the blood-brain barrier, and we've made advances on understanding how different materials and proteins can permeate cell membranes to do targeted drug delivery in different and new ways. But we still don't have the ability to really arbitrarily make whatever shape we want from whatever building blocks we want at whatever size that we want. And that's something where we're chipping away, but it's always a little bit out of reach. And I think that it's simultaneously an area where there's been so many wonderful big discoveries, but there's still this little thing that reminds us that we don't have arbitrary, perfect synthetic control over these tiny building blocks in the way that we might wish.
Mm-hmm. Superb answer. Other than plastic, what do we currently use that you think will seem primitive in 50 years?
Fossil fuels.
Okay.
Because we've got a limited supply, we know that burning them and releasing carbon dioxide into the atmosphere exacerbates changing weather patterns across the planet, and that's not good. And there's some estimates, and these keep getting updated. So I don't know the most recent ones right now, but there have been estimates about, like, if you took all of the coal and all of the oil that we know about that is left on the planet, and we only used that instead of solar, instead of nuclear, instead of wind, if we only used these fossil fuel sources to power the whole planet, instead of all of the other energy sources, the estimates are usually on the order of about 30 years, which is way lower than most people expect. Way lower. And so, like, that's a fact that's worth dwelling on for a second. And also, we keep discovering different kinds of oil reserves and inventing technologies that allow us to get to oil reserves that weren't previously accessible. So those are parts of why those numbers keep changing a little bit over time. But fundamentally, there is a limited supply of fossil fuels. And I think that hindsight will show that we maybe transitioned off of them too slowly compared to what could have been done.
If I may, and you can feel free to take a rain check on this, do you think that's just a case of money talking?
Yeah. It's, well, so...
Or it's just there, it's still convenient. It still gets us to work. It's,
money choices and policy choices are inexorable from each other. So we do a lot of work in my lab on organic solar cells. The same thermoplastics that you can use to make better airplane wings, you can also use to make solar panels. You can make solar panels out of plastic, and we think that we might be able to print them at very low cost if we get some economies of scale and figure out the right ingredients and the right processing protocols so that you'd be able to print a solar panel kind of like you make a newspaper from roll to roll manufacturing. We think we can do this in a way where eventually the energy, the cost of making the material will be so low that the energy that it generates will pay off that original capital investment on the order of days to weeks, instead of like the 10 to 15 years that we have for silicon solar panels. And so people say wow at that. And there's also this reminder that we would only say wow about that because of the current cost of silicon solar panels. But the cost of silicon solar panels is in part a policy choice that we make together. So the average length of home ownership in the United States is 9 years. The average return on investment for a silicon solar panel is 10 to 15 years. And so because of that disparity, homeowners are unlikely to buy silicon solar panels, and put them on their house because they're like, well, I won't get the return on investment for this capital cost of $15,000 to $20,000. We can have tax incentives for making that cost lower. Those are policy choices that we can make to incentivize behaviors that we agree on as being beneficial ones. And maybe we just haven't had that agreement, and that's also valid. But also if we all just put silicon solar panels on our houses now, then when you moved to a house in 9 years, it would have silicon solar panels, and you will have benefited from that investment that everybody put in. And so there's a technologist side of me that says, Eric, your plastic solar panels are just moving the problem. Like there's going to be recycling problems with this. There's going to be microplastics problems with this. It's not obviously better. It's not obviously better than just having good silicon solar panel policy today, even though it's a really great sales pitch, and we learn a lot about polymers that we can apply to carbon fiber composites over here. So it's science is worth doing, but I don't know that is the right technological answer for green energy production when we've got silicon right here. That it's pretty great. It's pretty great.
I'd like to shift to education specifically. In the extensive dealings with simulations, I mean, you said you teach undergrads, correct?
Yeah, and grad students.
So I guess this pertains more to the undergrads, but you hear material science and then they're eyeball deep in simulations and computation. How often do you encounter, oh, hell no, like I'm out? I mean, they know what they're signing up for initially. I get that, but am I right in assuming there is some?
Yeah. So I think once students have declared material science and engineering as their major, we don't see that anymore. But I teach an introductory class, Material Science 101, Living in a Materials World, that fulfills foundations of natural sciences requirement across the university. So every student needs to take one of these foundations of natural sciences courses at some point in their college career. And Many of them, on the order of about 200 a semester, will take this Living in a Materials World course that I teach every other year or so. And there's definitely students in there who are like, absolutely not. I'm only taking this course because I have to, and I heard it was interesting.
Okay.
But they find different rationale and justifications, some of which I think are well-informed, others of which I don't agree with, for why they might not pursue a career in material science.
How has the breakneck speed at which technology and software and hardware is moving shifted how you teach, if at all?
That's a great question. I think there's a few different layers to that. I think one is that fundamentally there's no substitute for, okay, wait, before I answer this question, I'm gonna ask you a question. What does a teacher do?
If you're asking me, Ellis, personally, if I can say two actions, inform and inspire.
Okay, great. Inform and inspire. I have a mental model that's not orthogonal to that, but different. And it is, I think that teachers, our role is that of a mental model diagnostician.
I was going to say that.
And what that means is, with some relative expertise in an area like material science or simulation or mathematics, my job is to understand how an expert organizes information and applies that to solve problems, to learn things, to get something done, and figure out where you as a student need more information or need more connections or need to organize information differently so that your approach moves towards that of an expert. My job is to help students become self-directed lifelong learners that are critical thinkers. And en route to that, my job is that of a mental model diagnostician. It's to figure out how are you thinking about things and what are the ways that we can add connections and pair connections between the concepts that are in your head so that you're moved closer towards being an expert. And I think that to do that, we need to understand our students. We need to understand how their mental models are structured and provide feedback on those mental models. And so the breakneck speed with which things like large language models are being developed and deployed, and the accessibility to high performance computing, and the availability of content management systems and learning management systems to assist us in the classroom, those change the shape of the classrooms that we are in. But fundamentally, if we are able to figure out how our students are thinking about things and be able to update their mental models towards being experts, we're doing our job. And that is something that takes time and takes effort. And there are elements that we can outsource to different automated tools or to teams of humans that are working together and teaching a course, but also at the end of the day, you still need somebody to care about your learning and understanding where you are and where you want to go, and provide that guidance and feedback that helps connect those dots.
You've taught hundreds of brilliant people who've gone on to do equally brilliant things. What's a skill or way of thinking that great material science possess?
I think fundamentally being curious about how things work, being skeptical and unsatisfied with superficial explanations, like that toddler that just says, why, is a really great characteristic to have in someone who can grow as a learner and a thinker. And I think that all of the students that come through our program are not just in it for the money, which is quite good at many of these companies, but they want to understand how these cutting edge technologies work so that they can help people. And so there's a maybe I can say that there is a pattern of curiosity and caring that I think we see across all of our graduates, in different levels, from individual to individual. But I think those two characteristics are consistent. But I think your question was of skill. What skill makes a good materials scientist? And
or trait.
Yeah.
It can be hard or soft skills, right?
Yeah.
Like either.
Curiosity, caring, and maybe skill. Like if you can take good notes, then it becomes tangible, the things that we talk about. Yeah.
What has your teaching and administrative work taught you?
On the teaching side of things, I think decades of teaching have reinforced how important timely feedback is. It is really easy to get overwhelmed by all of the different elements of being an educator and a professor today at a university. And it's easy to take like another day before grading homework compared to like submitting that $7.5 million proposal. In the moment, that proposal seems more important. But if we wait too long to provide that feedback, we're not fulfilling that role as mental model diagnostician efficiently. And semesters have a finite amount of time. We've got parameters on when things start, when things stop. And I think that one of the things that I've learned across 11 years of professional teaching is that timely feedback, however concise, is really, really special. I've also learned that there is no correlation between the faces that my students are making and the course evaluations that I get at the end of the semester. Like I'll get course evaluations that were like, this was the most inspiring, amazing class I've ever taken. Professor Jankowski was amazing. And like I had 15 weeks of resting bitch face and like nobody smiled one time. And I had no idea that you enjoyed this at all. You could have nodded once this whole semester. So
something book by its cover. It's great.
And on the administrative side of things, I think that some things that I have learned are that I think even if you take a whole bunch of really brilliant people who are so capable individually, putting them into a complicated system with a bunch of different things pulling on their attention and a bunch of different reward structures that spans multiple disciplines, multiple academic units. Even brilliant people will create inefficient systems that slow our own work down, and that there's something to be said for simplifying rules, and someone needs to be vigilant about minimizing bureaucracy. I think that is like I just saw the predecessor to the CIA had a sabotage manual that was just declassified. And there's a section on sabotaging organizations, and the guidelines for sabotaging organizations are things like always bring up a decision that was made at a previous meeting and question the advisability of that decision, and make sure to talk at length about it, and to make sure that we go through official channels to resolve this decision and revisit it. And like you go through this list of things to sabotage organizations, and you're like, that's Joe. I know that guy.
This is Tuesday.
And to see like those patterns of behavior emerge from really well-meaning folks who care about students, who care about making discoveries, I think reinforces the importance of being vigilant about trying to minimize friction in the organizations where we're trying to do good.
I'm going to go to 10,000 feet here. There's a great quote often attributed to Galileo. The goal of education is not answers, but better questions. What questions are not being asked enough or properly by the American education apparatus?
I don't know how to frame this as a question, but we've taken the play out of math education. And I think fundamentally doing mathematics and then applying that to engineering and learning in general is one of play and pattern recognition, like making jokes and funny games that is absent from a lot of K-12 education and a lot of university education. There's a really great old essay called Lockhart's Lament that frames this idea where if we taught art education like we teach math education, it would look like in your first year, you get to learn the names of the different brushes. And in your second year, you'd learn the names of different colors. And in your third year as a student, in third grade, we would learn about the different kinds of canvases that exist. In fourth grade, you'd finally get to put your paintbrush into a bucket of paint and apply the first strokes to a canvas. It's silly how we separate different elements of math education and remove the play from it. Whereas the first thing we do in kindergarten is get some finger paint and toss a bunch of toddlers in and let them go play inside of this system to explore, like, what can we do with our fingers and paint? Like, what can you do with a paper plate and some scissors? Like, what fractions can you cut into a paper plate with just folds and scissors? Like, you can play with that idea, and it turns into serious math after you play around a little bit. But like that specific example came out of second grade. We were in a classroom where we had drawn pizzas on paper plates, and we were going to cut these paper plates into different fractions. And the kid to the left of me was assigned 1/2. So he folded his plate in half and cut along that diameter and made a perfect set of halves. The kid to my right got 1/4, and he folded his plate in half and then folded that crease along itself to make perfect quarters, and he cut his plate into quarters. And I'm sitting there as a second grader, and I was like, how am I gonna fold thirds? And I couldn't in that moment, and I think I eyeballed it and did as best as I could. But that puzzle sat with me for decades. I was bored at a meeting at Dow Chemical in Plaquemine, Louisiana, and I was sketching in the margin just like playing around with that idea. And I figured it out. I figured out a sequence of folds that you could make without any other tools, and to be able to draw the lines that you could then cut along to cut a plate into thirds. And I wished that we had gotten to play with that idea more in second grade, and I could have resolved that question in that moment. But like we didn't have time to play there with that mathematical idea.
Wow, what an illustration. Dr. Jankowski, I want to be respectful of your time. We're already approaching marathon status. I have a brief section I'd love to explore before we close.
Sure. Once I stop choking on my
with
tea.
our lightning round, unless you have need to call the EMTs, chaps. What is Story Collider and how did you get involved?
Story Collider is a national storytelling nonprofit that shares true personal stories around the humanity of doing science, that reveals the human pursuit of discovery through true personal stories on stages. They happen at bars all over the country, and some of those stories told on stages end up on the podcast that releases a pair of episodes every Friday. I made dinner at my friend Joe's house every Thursday night of graduate school, and Joe was subletting a room to a stranger. That stranger happened to be one of the founders of the Story Collider. His name was Brian Wecht. He was a string theorist postdoc at Michigan when I was a graduate student at Michigan. And Brian asked me to pitch a story for a show at the Ann Arbor Public Library. And I told a story, pitched and then told a story about accidentally getting my high school biology teacher fired by telling jokes at a presentation to the executives of Dow Chemical after we sampled the water upstream and downstream of Dow Chemical as part of a high school biology project. And so I told this story about making this mistake, like having big consequences for this teacher that I really adored and learned so much from. And it was so different from telling a story. When we give scientific technical talks at conferences, because skepticism underpins truth-telling and discovery, there's a little bit of a combative relationship to giving a technical talk. Everybody in the audience is trying to look for logical flaws or methodological flaws in your approach that might undermine the connection between the results and the conclusions that you're communicating, because they want to know what's true. We want to be able to believe and vet the discoveries that we make as a community. And so it's kind of stressful. It can be kind of stressful. Certainly if you tie yourself up personally with your results, they feel like personal attacks.
Sure.
And so I had this experience of telling a story about making mistakes. And at the end of it, there was applause, and a whole bunch of people came up and like had great conversations after this story. But like physically, it was the same as giving a technical talk. I stood up in front of a bunch of people and I used my mouth and I like exhaled air and made noises with my mouth. Here I was talking about making a mistake, and it built community and like revealed some realities about training as a scientist. Mm-hmm. Whereas often scientists will work very hard to like obscure the results that or mistakes that they made, or maybe not even know that they made mistakes over here. And so it was fun, it was productive, and it showed me that there's something missing in our training of scientists, that in our pursuit of truth, we often cover up the truths of the stresses and realities of growing into a discipline where we don't feel like we belong. Yeah. And so I brought the Story Collider into one of the first courses I taught at Boise State to help our thermodynamics students tell true personal stories about thermodynamics. And that we surveyed some attitudes about those students that suggested maybe that this one assignment might help students connect with their major better, that it might help with student retention. And we got a National Science Foundation grant to study that across all of the different departments in the College of Engineering. We got another National Science Foundation grant to study that for graduate students across the university and at Utah State. And now we're working on another grant to see if we can spread that to a bunch of different universities in the Pacific Northwest.
What a growth tale. Is every participant, well, let's speaker and audience members and I guess podcast listeners, all scientists? This is clearly open. I mean,
so like the conceit of Story Collider is that if you have ever learned anything, if you've ever effed around and found out like you're a scientist, and
so you don't have, there's not a minimum number of citations or
no,
okay,
yeah,
okay, super.
And the performers come from all walks of life because everybody is a scientist. But it's often, if you're not in a PhD program, you don't know what it looks like to be trained professionally as a card-carrying peer reviewer. And so revealing that and the different elements that people have learned, different ways that people learn things in different areas is a wonderful community building thing that I think we need more of.
Who is the greatest need for better storytelling between science, technology, or universities?
I think we still have inaccurate public perceptions about like who is science. Sixth graders still draw like bald men with glasses holding beakers, and that's like a very like chemistry specific public perception of like what and who a scientist is.
Yeah.
I also think that there's inaccurate narratives around the value of a college degree today. Some of those are justified, some of those I think are not. And I think that similarly, there are narratives around big companies and technology companies and technologists individually that miss nuance around how decisions are made, how technologies are built, how they're deployed, the impacts that they have on our communities. And I think that there's, maybe the right way of saying this is that in addition to having better publicity from the perspective of science, or a university or a company, I think there's certainly an opportunity for better discourse and conversation and like engaging with the possibility that one is wrong and correcting one's behaviors and ideas when presented with evidence.
Yeah. It's hard task for some. Most.
Yeah. But as scientists, we have a privilege of being wrong all of the time. And so like maybe one takeaway from this conversation is that you get acclimated to being surprised and being wrong. So you get used to being skeptical and changing your mind all of the time because you're always wrong. And that's how we know that we're learning is by
that's right.
Consistently being wrong.
If that is an advancement, I don't know what is.
Yeah.
Okay, Dr. Jankowski, we like to wrap with some fun, random, quasi-lightning round questions.
Okay. Yeah, I failed at the last one. I talked for like 5 minutes about story.
No failure at all. What's your earliest memory of physical stuff wowing you?
Physical stuff wowing me. I remember spinning a bicycle tire that was on training wheels and like spraying the sand up next to the side of my house and having fun. That's a very early memory about stuff awing me that I can remember. Yeah.
Agree or disagree? Idaho potatoes really are all that.
Agree.
What's a scientific consensus you're skeptical of?
I don't know. All of them.
A true rebel.
No, that's a responsibility.
You're a coffee enthusiast. My homework is correct.
That's right.
Through a scientist's lens, rank the top 3 ways to prepare a cup.
Oh, scientific lens. I think espresso has the most control over pressure and temperature and grind size, and so in some ways is involves the most science. Pour over is a subset of that I enjoy the most. And
that is your beloved, the pour over personally.
Yeah, and maybe a vacuum, a siphon pot, because it uses negative pressure at some point, gets to rank up there. Yeah.
Couldn't have got a better response. You're also an avid cyclist. Uh-huh. Given the prevalence of steroids in the professional ranks, was Lance Armstrong wrong to juice?
Ooh, that's a really hard question. Lance broke my heart. I don't think that you should cheat at whatever sport you're doing. And also the reality in that moment was that lots of teams were doping in various ways. But also he was a jerk about lying about it. So those are different difficult things to disentangle around Lance Armstrong. But he got me into cycling. I ran a cycling team for years because of Lance Armstrong. Humans are multifaceted, complicated, and eventually will let you down. And I'm going to let you down someday, Ellis. Just like Lance. Not just like Lance. I'm not going to do any doping, and I'm not going to cheat at anything. But maybe I won't. Maybe I won't. Maybe I'll get hit by a bus.
Those syringes you walk in with. If we encounter aliens, what is your speculative bet for where they're most advanced? Energy, computation, or materials?
If we meet aliens, I think they would have to be, materials, because it underpins energy, and consequently they'll be able to manage information and computation well. So I think materials.
Great. Last question, Dr. Jankowski. What are you most excited about for 2026?
The thing that first came to mind was I'm excited to ride my bicycle more this year. I'm so excited about the opportunities that exist to work for our students, connecting them to opportunities in Taiwan, in the semiconductor industry, to coordinate across the state in terms of education, to work with the students that are coming up into the university to show the value proposition of this degree, to help our students have a great time in the classroom. All of those things are just helping people around these scientific inquiries that I get to have fun doing as a job. So I'm just excited. I think I'm just excited, Ellis.
It's palpable. Seriously. Dr. Jankowski, thank you so much for coming on the Recap Podcast. You're a beacon of knowledge and inspiration. Keep it up.
Thank you. Thanks for having me.